Cool. Hello, everyone. This is Arjun from Connext. Today we're going to walk through the protocols. So the assumption here is like you've already watched the contract walkthrough video or understand how the contracts work. This is the Offchain protocol, which produces commitments, which then go on chain. And ideally, this stuff should mirror the on-chain work. Basically, like just replicate the same kinds of ideas, except do it off-chain in the happy case. So everything in the protocol fits into this, is a part of this, like, basically it fits into these 4 files, which is sync, update, validate, and vector. And then there's some utilities. The vector.ts file wraps everything. And it's a class that takes in a bunch of services, and these services are passed in from like the node, from the node layer down to here, so that way you can like utilize them the same way across every layer of the stack. We pass in a messaging service, lock service, store service, signer, chain reader, external validation service. What is the external validation service?
That's so you can inject your own like contextual validation, like
Got it.
as a router or whatever.
Got it. Okay. So yeah, external validation service and then a logger. You call this class, so you instantiate this class and then call connect, and we do connect because there is we can't actually, like, there are async functions as part of setting this up which cannot which can't be set up as part of instantiating the class. So
and be in your constructor.
Yeah, exactly. We do await new vector inside this, and then this calls setup services. This is, I'm assuming that this is just taking in the external validation from the validation service and like mapping it to these methods. Is that correct?
It's setting defaults.
It provides a default that doesn't do any validation, but conforms to the interface.
Oh, I see. Okay, got it. Cool. Let's jump into the setup services, so that way we have some context on what's going on. So here, we create we basically set up like listeners. This is the messaging service. Every time we receive a protocol message, we let's see. We get the we do some error checking. We get the message value. We validate the message, or validate the params in the message, and then return. Is this? I guess this is a bit different than what we were doing before here, right?
Yeah. So all I added here from what we were doing before was just like, because we're receiving this over the wire, we want to make sure that the updates that we get are properly structured and have the proper fields. So this doesn't actually do any details validation because Typebox has some limitations there when you get too crazy with the nested types, but that's done in the actual validate file itself.
Got it. So this is pretty cool. You're using validate params everywhere, which means that you didn't have to like have separate validate updates and validate param functions.
Yeah, so this is a slightly different validate params. We could probably rename it to something called like validate API params or something, or validate schema, because it's just validating that all of the params are present and have the correct format. So it'll do string validation on public identifiers, for example, to make sure they're correctly formatted.
Got it. Okay. Cool. And then at the end of that, we just call sync out inbound, which is something we'll get to, which is kind of like the meat of the protocol. And after that's done, we post things to, we post like results to as an event. What are these to-dos?
Let's see. Is alive is 52.
Okay.
53 is probably restored. Oh, no, 53 is closed. And yeah, 54 is restore.
Okay, got it. Okay, so there's basically just a couple pieces of this protocol that need to be implemented separately, which are like features that can be added on top. So we sync the latest state before starting. We handle any disputes to check to see if there's any disputes going on chain. This basically will stop you from running the Offchain protocol in case there is a dispute going on. And then we don't have the built-in capacity to automatically respond to disputes right now. It's something where we don't yet know whether that's something that we want to do by default anyway. We might have to have that be like a separate service. And then once that's done, we return the object. So now you have like a setup vector instance that listens for inbound connections. Cool. So after setting up the service, the next kind of step, so we return this node, and then users can call, or like the higher level code can call, basically call one of 4 update types, so one of 4 functions that let you do, that let you manipulate the state. These are the core public methods. There's setup. Setup creates a channel and like returns the channel address. There's deposit. Deposit actually doesn't take in any funds or anything. It just checks to see where. Sorry. It checks to see what the on-chain, like what the difference is in the on-chain deposit amounts, and reconciles that against the off-chain state. So the assumption here is that you have already deposited into the multisig. You've already sent funds to the channel multisig, per the stuff that we described in like contracts earlier. Create this creates a transfer to a counterparty, and so this like sets up the logic for a conditional transfer, locks up some funds within the channel between, basically like escrows them between you and your counterparty, and then those funds can only be unlocked depending on whether or not the logic within the create was satisfied. And then resolve is the satisfies this logic. So basically the params that you would pass into create would be a pointer to some on-chain transfer definition, and we can cover kind of like how that gets called, and then along with some like an initial state, and then resolve will take that initial state, will take in a like some params used for a state transition. We'll apply that state transition to figure out what the final set of balances are, and then we'll update your off-chain balances to reflect the results from resolve. Now, one thing you might notice is that in every one of these cases, we're actually just calling the same lower level function. So we're doing some basic things here, like getting the multisig address in the case of setup. We're always validating the params, and then we're kind of manipulating the params before calling this .execute update. All of these functions funnel into this execute update method, which starts over here. So execute update is kind of where the meat of the protocol flow happens from the sender side. You take in your params. We kind of manipulate the params slightly if it's a setup update. So in the case of setup, we ensure that like Alice identifier, so the identifier of this person is this public identifier. Actually, this is a bit interesting. So why do we do this? Oh, we do it because the caller of the setup has to be Alice. Okay.
Yeah.
Yeah. Okay, that makes sense. And then if it's not a setup update, we check. We get the Alice and Bob identifiers from the channel itself. So this is a way of kind of bootstrapping the channel, figuring out who the actual initiator and responder are. Then we set up these variables, and we call, we acquire a lock from the lock service, we execute the locked operation, and then we release the lock. So acquiring a lock, basically, we use a locking system between both parties in the channel to as a mechanism for deciding who makes the next update. So basically both parties would like queue up on this lock and would execute the lock serially. So this acquire lock could take, if there are other locked operations pending, could take some time, but this is what like manages concurrency control in the channel and ensures that you can only have like one update happening at a time. You don't have several updates happen and then your state gets all messed up. And so within this lock is where kind of the like core part of the protocol is executed. Let's jump to locked operation. And locked operation calls this lower level sync outbound function, which is where like the sender side of the protocol happens. So let's jump into that. Everything else is kind of just like handling errors, things like that. So jumping into sync.ts. Sync.ts is where like most of the important logic is. There's basically like in update.ts we generate what the update looks like. In validate.ts we validate like either an incoming update or incoming params. But sync is where we take an update, send it to the counterparty on the outbound side, and then on the inbound side we get an update and figure out what to do with it. So sync outbound gets the context from store. Or I guess we are now doing this instead of passing in the context itself, which is probably good. Yeah, seems like it's a good thing. Then we validate the params and apply an update. So we basically take in the params that we passed into this function and then like create an update from it. Could jump into this function really quickly. So validate params and apply update takes in validate update params, which itself checks to see if let's see. This checks to see if the if it is not an update, if it is not a setup update and there is a previous state, then this will throw an error. If the previous state.
So this function just goes through and does all of the update for any like set of update params. It checks it against your previous state, existing active transfers, and the initiator of the update, and goes through and validates everything contextually.
Okay, got it. So if the previous state is in dispute, then it throws an error. If the previous state, if there is a previous state and the channel address of the previous state is not equal to the channel address that you've passed in, that also throws an error. Basically, we're just checking to make sure that like the things that are passed in make sense against what's in your store. And then for each type of update, we do further validation. So in the case of setup, we check to see that the calculated address is the same as the one that we've derived on chain. So we're getting this. So we're getting the channel address that we're passing in here is generated from vector.ts, right? Because it's generated in this setup function.
Right. So the trick I did was I noticed that as we had these two separate inbound function, validate inbound, validate outbound functions, we were duplicating a lot of code. They would all be simplified if I just like converted the update that you got over the wire once I validated its schema into params and then just ran through the same param validation code. So because there's a chance that this could come from something over the wire, you still want to verify it. We could say, if you're the initiator, skip this, but it's not that much of a hit.
Yeah, we can, if it's like if it optimizes latency and stuff later, we could do that. But right now,
right,
like this might, maybe, I mean, we could also optimize latency of this by just like caching this data, and then that way, like if you're doing it twice, then you don't have to do like an actual chain call twice.
Yep.
Cool. So we check to see that the timeouts are within reasonable bounds. We have like a minimum and maximum timeout defined. We check to see that the counterparty identifier is equal to the we check to ensure that the counterparty identifier is not the initiator identifier. So because this is a setup update, you have to be the initiator if you're calling this. And then same kind of pattern goes for deposit. So for deposit, we check to see if the asset ID is actually an address, if it's formatted correctly. That's pretty much the only thing on deposit. On create, we check to see that the asset ID is actually a part of the channel. So this asset that you are trying to transfer does have a balance in the channel. We should check not only that it's a part of the channel, but also that it has a balance. But I guess that will happen.
We do that down
here. Okay.
later, yeah.
Okay.
You can't even get anything if you don't have the asset in your channel, so you may as well just throw.
Okay. Yeah, that makes sense. Okay, so and then we have we check to ensure that this transfer ID is unique and it's not already active transfer. We verify that there is sufficient balance to create this transfer. Okay, there it is. So effectively, like whatever amount you're trying to put into this transfer needs to exist within your balance already. And then we verify that the timeouts are within the reasonable bounds. And then we lastly check we basically call the create function within the transfer definition. So we cover this in the contract walkthrough, but basically like each transfer definition is like a state machine that describes how like the conditions for locking up a transfer and then how you can resolve them. And then there's two functions within that state machine. There's create, which is entirely stateless and only just has like a bunch of validators. I guess they're both stateless, but the create function just validates the initial state, and then the resolve function actually applies a state machine, returns a balance. So this create would check to see if the initial state and the initial balances passed into this match the transfer specific validation that is described on chain. But the reason that we do this is that it's not really possible for us to know a priori what the specific initial state validation will be for a given transfer definition. And we want to allow people to support their own transfer definitions without requiring any changes to off-chain code. So in this case, what we're doing is we're writing the same validators just entirely on-chain. And then, yeah, so we check this. And then lastly, we do something similar for resolve. We make sure that the transfer exists. We check to see if this transfer resolver is an object. We fail if the initiator is not the transfer responder. So one thing that we hard require is that like the person who calls resolve must be not the person who created the transfer. So it must be the counterparty of the person that created the transfer. And then lastly, we fail if the transfer has a resolver already. This means it's like already been resolved. Why are we not checking the actual resolve here? Oh, I guess that happens in generate update. Okay. It'll happen in validate actually. Calling the
checking what about it?
Calling.
Oh, that happens in generate. Yeah, that happens in generate. Because you get a return value from that. You get a final transfer balance.
Yeah, but how is that checked on the counterparty side? Like for the person who's receiving this update,
they both so they'll convert the update to parameters, go through the update validation, and regenerate the update, then check the signatures. So they'll just call it completely independently. Yeah.
Got it. Okay. And then lastly, if you're the update sender, you perform some external validation. So you check to see, let's see what this validate outbound does. Oh wait, this is the thing that's passed in. So this could be any potential like passed in middleware validation that you have specific to a transfer. That's not a part of this code either. Cool. So that's kind of that's the core validators. And then we have, so back to the validate params and apply update. We validated the update params, then we do generate and apply update. This is like kind of the second part of it. Generate and apply update goes to the update.ts file. This creates an update associated with the parameters that were passed into the vector module. So if, basically there's just a switch statement here where we generate different kinds of updates depending on what update we want to create, and then we apply the update, generate a commitment for it, and then lastly return like a new updated state. So generating the setup update takes in, basically we get the public identifiers and participants of this channel, and then we generate this channel update of type setup, which takes in which has a nonce of 1, and then all of these remaining params. So I guess here we always default to having asset ID address 0 no matter what.
Yeah.
Should this be
For like
array?
an initial 0, like 0 index thing.
Should this be in an
I think-
array?
Well, that's just one update,
No, this
right?
is for an update. So this is all
Oh,
the
I see. It's
generate
not the
update
state.
functions.
Okay. Got it. Yeah.
So
Right.
that will instantiate the channel with address 0 and balances of 0
Okay.
as with an array.
So then
right?
you go through and you take that update and you apply it, and then you get a nonce 1 state that you can properly dispute.
Okay.
That
Right.
has like address 0 in the first instance of the array.
Okay. So generate deposit update. So for the deposit update, we get asset ID from the params. We check to see if the asset ID already exists. If it does exist, then we check what the existing channel balance is, and then we calculate the process deposits of this asset ID so far. So basically, if the asset ID exists, then how many deposits have we done so far? This comes directly from like state.process deposits. Then we call this reconcile deposit utility, which is actually pretty important, so we can jump right into it. So the reconcile deposit function checks the on-chain total deposited. So we kind of just alluded to this to describe this in the like contracts walkthrough, but what we do here is we calculate the amount that has been deposited and is owed to each party based on kind of like a combination of on-chain quantities, which are like the total amounts that have been deposited by A and B, and then the amounts off-chain that have been processed so far. So the difference between those two has to be equal to the amount that needs to be reconciled into the deposit. So we get the total deposited by A, we get the total deposited by B, and then we subtract both of those from the amount that has been processed by A and B, and then we lastly calculate the new balance. So we add this deposits to reconcile, which is the amount processed by A and B, into the amounts, the balances for each party. Jumping back to update. So after that, we just plug all of these things and return an unsigned update. So for generate create update, we get the transfer. We get the like transfer definition. Interesting, actually. This is like the registry entry from the on-chain registry contract of all of
Yes.
the registry transfers. Yep. And this,
Well, specifically
we're getting this,
that registry transfer, but yes.
Okay, got it. We get from that we get like the state encoding and resolver encodings for the specific transfer. These are on chain and like a part of the transfer definition itself. We create the initial state hash. So that basically just means we hash the transfer state that is passed in against the state encoding. And then we set the counterparty address and create this transfer state. As part of creating this transfer state, we also generate like Merkle tree data. So basically what we're doing here is we're adding this transfer to a Merkle tree and generating like both a root and then like the proof, which is all of the other separate data aside from this specific initial state, specific hashed initial state. And then all of that gets added to this update. And then lastly, so generating resolve update, we first do the opposite of what we did up here. So we generate the latest Merkle tree data and get the Merkle root. And we do this using a passed in, should be using a passed in root and proof, right? No, actually, I guess we're getting all of the transfers and then going.
Yeah. So we
Okay.
regenerate it from the updated like active transfers without that one.
Got it. Well, we might have to figure out how to like optimize this, because this will end up taking time.
I don't think it's possible to like change the Merkle root by just taking one out, right? I think you'd have to regenerate it.
As
you
far
have
as I
to.
know, yeah.
Yeah,
Yeah, but we can.
that's something to think about.
There's probably existing libraries that we can use for this that will be much more optimized than anything that we could build in house.
It is using
We
an
are
existing
using,
library.
yeah, we are using a
We are
library.
using a library. Oh, okay, never mind.
Yeah,
Yeah, I just have
we're
it in the
using that.
utilities function because, like, I don't know, you need it in the contract tests too.
It's using
Okay.
like Merkle.js or whatever, so I think
Yeah.
it should be pretty good.
Okay, nice.
But yeah, we can't. I agree that it could take a while. So if there are efficient ones, or we should make sure to time that step or something.
Yeah,
Yeah.
we can like flame graph all of this eventually. Maybe like it within the next couple of weeks. Cool. So get the final transfer balance from the contract. Then we should definitely like flame graph the protocol specifically. So just like run the protocol tests and then like flame graph them and see how like what
Totally
within this
agree.
protocol is actually taking a lot of time, because this is most of the actual execution.
Yep.
So yeah, so we get the final balance. So this calls the on-chain chain service resolve function, and that would return a final balance. Both parties are doing this, so we could have both parties individually do this, generate the same update, sign it, and then check the signatures against each other, and then that effectively acts as a validation of the step between both parties. And then lastly, we get the updated channel balance. So basically, this is just like a helper function, which takes in the update type, takes in like the transfer balances and then reconciles them against the existing state. And then we package all this into an update and return it. Generate base update just as a helper function, which just like handles the like basic things which will always be updated. So ensure that the like channel address is the same, set the like the update type, the to and from identifier, and then like increment the nonce. Cool. We also have these helper functions which are called above in a nested way. So reconcile balance with existing, basically like updates the balance array. So one thing that we have within the structure of the state here is that like balances are an array and they're indexed at the same index that the asset IDs are. Asset IDs array is indexed at. So when we want to reconcile balances, we have to like find the index in the asset IDs array, and then update that specific balance. And we do kind of the same thing with process deposits. Cool. So
I think I made a helper for that in another place, by the way. Just
oh, nice.
yeah, we can.
I think okay, yeah, maybe we should figure out how to reconcile those two.
Right.
So we've generated and applied an update. We respond with an update response. That goes back to the sync.ts outbound. So we've completed this validate params and apply update. If there's an error, we fail explicitly. We get all of these updated values from the update that we got, and then that is dispatched to the counterparty. So we attempt to send this to the counterparty. I'm assuming that the retry and stuff is built into the messaging service now.
Yeah, it's a retry of sending messages.
Yep.
Like specifically sending messages, yes, but like retrying that specific update and responding to errors is obviously right here.
Right. Okay. So within the send protocol message, we'll like retry a few times if there's no response. And then if we get a response and it's an error, and the error reason is that it's a stale update, i.e. the update that you sent is already is basically like more than one update behind the counterparty. It means that you are behind, your channel is behind. And so then we would sync and retry. So syncing, what we would do is get the update that was passed in as part of or passed back as part of this like inbound channel update, or like this inbound channel update error. And then we would sync that against our local state. So doing that, let's see, jump into this function. So doing that will take in the received error, the attempted params, your previous state, active transfer, store service, chain reader, external validation service. We'll call this sync state function, which I guess does some validation. So we can't do this for setup, obviously, because setup is the first update. We also check to make sure that both signatures are there. And then we would call the same validate and apply an inbound update as you would call for sync inbound. So we'll get to that in a bit. It's pretty interesting because basically if you sent an update, you were behind, then you end up being the one who syncs an inbound update in the same way that it's kind of like you are now receiving an update because your counterparty has now given you more state that you need to catch up to. Cool. So we did sync and recreate an update, and then once that happens, or once that's complete, that means we are now up to date, and we can now try sending this protocol update message again. So now we'll try sending this update one more time. One question I have here is do we need to regenerate the update itself?
The update params? Yeah.
Yeah.
Or you should, because you basically have to go back through the parameter validation.
Yeah.
If I'm trying to create a transfer, and I want to send one that's immediately invalid, so yeah, you'll have to recheck once you've synced.
So this won't work, right?
What do you mean?
So this where is this? What is this sync object? Sync result.get value. So what will this return?
It should return the same thing apply update does. So an update, or generate and apply update. So an update, an updated channel, updated active transfers.
Oh, I see. So sync and recreate update also handles the process of ensuring that your previous the update the params that this was called with are also now going into the next update.
Yes.
So okay.
So it
basically
takes
I'm
in
syncing
the inbound
update
state.
N.
Yeah.
Right.
I propose at N, I'm behind. So I sync to state N, and then I propose again with state update N plus one.
Okay, got it. Okay, yeah, cool. So yeah, in that case, we could just basically dispatch this next N+1 update to the counterparty. And it'll be an automatic retry of the params after catching up to where the counterparty is in the channel. We do some error handling to ensure that if this does actually happen, we will hard error. And then at the end of everything, or I guess not at the end of everything. So then we get the counterparty update. We validate that the counterparty signatures are correct. Basically, at this point, because this is happening in the outbound, at this point, you are assuming that the counterparty has agreed to your update and has signed both states and has returned something that isn't an error. So at this point, you would validate both the signatures, and then you would save the new channel state to your store. If there was an error, or if the saving the channel state didn't work, you would also hard error here. Now we can switch over to the receiver side. So the receiver side, that's basically everything that happens is when you initiate an update, and then the receiver side, you are receiving an update from the counterparty, and you have one of a few choices. Either you are validating and returning, countersigning, returning that update, and that's in the happy case, or you're behind and you need to catch up, or you're ahead and your counterparty needs to catch up. So in the sync inbound, the first thing that we do is we create this return error function, helper. What this does is ensures that any error that we generate as a result of attempting to sync inbound is also returned to the counterparty. So both parties have context into the error. We once again extract the context from store. We do this instead of passing in because it's just a more consistent pattern. Then we have this algorithm, which I kind of described, which is if you're behind by more than 2 updates, your counterparty is 2 behind and they must restore. In general, you should never fall more than 1 update behind unless something explicitly got deleted from your store. So this should never really happen unless like something went wrong with your store, in which case you should manually restore your store. If you're one update behind, it means that maybe you dropped an update, like a message somewhere, and so we now need to like sync to get to the same state as your counterparty, and then process the update that they gave you. Or sorry, that this is for the counterparty is behind. The same kind of goes in your case as well. And then if you get an update that is the same nonce as what you're at, and it's a single signed update, that means the counterparty is behind again. If you get a nonce that is double signed, that means that you, if the states are the same, what does this mean? If the states are the same, actually. Oh, if the states are the same as what you have in your store. Got it. The counterparty is behind because they're returning a double signed update to you, which you haven't actually initiated.
Right.
And if the states are different, then that's really bad because that means that we've gotten into a state collision. Should really never ever happen. But if that happens, like that's something that we should immediately flag. And then this is kind of like the happy case, which is you've received a state, which is at n+1, which means that your counterparty has created an update and sent it to you. So now we need to verify it, like store and ACK. And then if you receive a double signed update, that is the counterparty acting an update. And this is like basically if you like, this basically means that you also call sync outbound, and this is just sync inbound picking up your own update like response. So this should also actually already be handled up in the outbound. And then if they are, if they're proposing an update that is 2 ahead, then that means you're behind, and now we need to sync state. And then if they're more than 2 ahead, that means that we need to restore. Cool. So how we handle this? So if diff is less than 0, so we check the diff between our nonces. If the diff is less than 0, less than or equal to 0, it means that we don't process this update. We basically just don't do anything except for return error here. If we are ahead if the difference between the two is greater than 3, it means that like this is not something we can sync, so we have to restore. And then if the diff is equal to 2, and we don't have a previous update, then we would return error because that should never happen. If we do have a previous update, then we should sync the state of our previous update. And then if we have an error with that, we return the error again. And then the assumption here is like you either enter into this like if block, which is where you are behind and you need to sync. And if you don't enter into this, if like in either case, regardless of whether or not you enter into this if block, at the end of it, you would validate and like apply the inbound update. And that's because at the end of this, you can be pretty certain that you are in the right place to accept a new inbound update. Your counterparty's nonce is now 1 ahead of yours. So you validate and apply this inbound update. This goes into a helper function, which we can actually just jump into right now since we're towards the end of this. So validate and apply inbound update. Validates the schema of the update. This is just checks to see if everything kind of looks correct against the types. We then, let's see, keep going. So we check to see that the nonce is correct. It's incremented by 1. We handle like double signed. We check to see if the update is double signed. We would validate these like other params. So this is what ends up getting used as part of the validate in like the sync inbound or sync outbound. Sorry. Let's see.
We don't validate anything. We just apply the updates and check the signatures are valid. And if the signatures are valid, we assume it's already gone through. And then so we exit early.
Oh, nice. Okay, got it. I see. So we do transfers, fine. Okay, so we check to see if the transfer is a part of this. If it's resolved.
Because in apply update, you need the final balance for resolve. So we're just getting that here.
Okay. I see. So yeah, we just apply the update on top of all of this. I guess this part might need a little bit more comments. yeah, we apply the update on top of this, and then check the signatures on that update against the signatures that were passed in from the counterparty. And then if that's done, we would, so on a single signed update, we would always perform this external validation. And so we would call this validate inbound function. That's like the passed in validation middleware. And then lastly, we call this validate params and apply update lower level function. Jumping into this, this does what we were doing before on the outbound side. So that's good. I guess it's good that this is, a lot of this is being reused quite a bit.
Yeah.
Cool. I think that was it on this. Yeah,
that's
so
it.
And then, yeah, we validate the signatures, and then we generate a signed commitment and return that signed commitment as part of this. That happens in the case that this isn't a double signed update. So jumping back into sync, at this point, we've validated and applied this update. We now have a new updated channel, and then we would save this channel state to our store, and then we would respond with this this new signature. Like the assumption here is like it's a second, like there's a second signature now that you're responding with, and you respond to the counterparty with that. And yeah, that's actually pretty much it. In the process of going through this, we've also jumped into all of the helpers in like update and validate. It seems as though, for the most part, there's like a lot of code reuse, which is good. And the general structure is that, like, for any update that we're generating, we call update.ts, and then anything that we're validating, we call validate.ts. So I guess one thing perhaps that we can work on is just like making sure that outside of this, like, we've documented these helpers well, so people understand what each one does and what each one's responsible for. And we could perhaps have like comments about these functions too. And then that way, outside, like in the protocol readme, we could just have like a flow diagram that says like, okay, we call this function, then we call this function, then we call this function. So people get a good idea of like what each step is along the way, because the details of each of these functions are actually relatively less important. Like, there's, of course, like, we need to make sure that we have like coverage on all the validation and stuff, but for the most part, the general ideas behind this should be pretty understandable just from like a flow diagram. So yeah, I think
There is a flow diagram actually in the README.
Oh, there is. Okay, nice. I haven't actually seen that. I guess I won't be able to see it here, huh? Okay. Well, I'll check
in that image.
Oh, there it is. Yeah. Okay. Nice. Cool. Is there anything else in here that I've missed?
No, that's it. It's pretty thin.
Yeah, I like that very much. I think keeping the Offchain protocol really thin is a really good idea, because like, this is good. This significantly reduces our overhead. Now, one thing to note is that, like, generally as part of the recording, like, this protocol, the idea behind this protocol is to like allow for facilitating updates in a channel between two parties. The core protocol code does not contain any context into like other channels. So like linking updates between channels and like doing like a multi-hop transfer is completely outside of the scope of the protocol itself, and that all of that kind of just exists in the router. So the router, like, there's like a strong delineation where the router is the one that kind of takes in inbound transfers and then forwards them to a receiver. But all of the actual base validation associated with that transfer, the router is just kind of like doing this blindly. And all of the base validation associated with that transfer happens within the actual protocol itself. And that is all specific to the transfer definition. So the transfer definition itself is pretty important too. Like, a part of the security of the protocol itself relies on making sure that like these transfer definitions are written correctly and don't have holes in them. So that's something that, like, for now, we're manually auditing any transfer definitions that like come in, or either that we create or that like anybody proposes. But eventually we'll have to like put together some good like security practices, perhaps make it a little bit like put up some like guardrails within the transfer definition contract itself, Maybe we could just like have some helpers and things like that, automatic like validation and stuff that ensures that you even if you implement it incorrectly, like there is going to be like a loss of funds situation, and we don't have to spend as much time like manually auditing everything. But that's probably a bit of a ways away right now. Yeah, other than that, seems like, I guess the other thing is like test coverage, which I think we could check against like the actual test coverage doc later. But I believe we have like every one of these validators tested, right?
That's the goals. So far, we should have everything, like every fail statement get hit.
Okay, cool. So yeah, I think as long as if we do that and we test these like lower level validators and update functions, this should be totally fine. I'm really excited to like do that and get that done, and then we could pretty much just like lock this protocol code and not touch it at all, except to like add in things like restore and is live.
Yeah.
Cool. I'm gonna stop recording. Thanks everybody.